AMD hardware ray tracing support has landed on PC with the RX 6000 series GPUs, and the benchmarks are of course already out there. But I personally am very interested in ray tracing. I want to get my hands on one of these GPUs to see exactly how it ticks and works. So in this video today, I'll be going a bit deeper with an analysis of the cost of ray tracing for a variety of ray tracing effects across some select titles. Basically, I want to look into the GPU cost on a per effect basis for ray tracing to give us a greater understanding of the difference between GPUs perchance, and hopefully a better understanding of ray tracing itself by the end of this video. In making this video today, I will be looking at the ray tracing performance of an AMD RX 6800 XT, specifically the Speedster Merc 319 version of that GPU from XFX. It's a slightly faster version than the standard model, with a boosted rated clock at 2340 MHz, or around 5% higher rated than the boost clock standard. But I've seen it commonly boosting around to above 2400 MHz, so around 7% faster than the standard model. All the tests of this GPU will be at 1440p, which I see as the increasingly de facto PC resolution these days, and will be compared and contrasted to an Nvidia Founders Edition RTX 3080. All tests will be done on a Core i9-10900K, which is the highest CPU I own, so that unfortunately means that there's no support for resizable bar at the moment for these tests on this AMD GPU, which I want you to keep in mind as it could affect these tests. In these investigations, I will also be focusing on the less commonly used millisecond rendering time performance metrics. Milliseconds of rendering time is pretty simple. Imagine a camera view pointed at a wall in some static game scene. When looking at that wall, imagine that an imaginary GPU is running maxed out and averaging 40 frames per second. At 40 frames per second, the average frame time looking at that wall is around 25 milliseconds per frame. This value of 25 milliseconds is what I am interested in this video, and the reason is important. For this video, I'm interested in the specific costs of turning on and off ray tracing between GPUs, or the cost of adjusting that ray tracing through options or quality sliders. Using percentages, frames per second, or percentages from frames per second is going to be less specific and less clear, and perhaps lead to less clear conclusions. What do I mean? Let's take a look at that same scene with two different imaginary GPUs. Like the last time, imaginary GPU 1 renders the wall at 40 FPS, while GPU 2 renders the wall at 80 FPS. Now let's turn on imaginary ray tracing in this fake example. With ray tracing here, GPU 1 now renders the wall at 30 FPS, while GPU 2 renders the wall at 48 FPS. If you're just looking at the FPS dropped in total, or the percentages, it looks like ray tracing costs 25% performance on GPU 1 and 40% on GPU 2 from the FPS numbers. I don't think these numbers are perfectly representative of what is going on. In reality, turning on ray tracing in this theoretical example costs the same on both GPUs actually. For GPU 1 at 40 FPS or 25 milliseconds per frame, it's going down to 30 FPS, which means ray tracing has increased frame time by 8.3 milliseconds to 33.3 milliseconds per frame. For GPU 2, it went from 80 FPS or 12.5 milliseconds per frame down to 48 FPS, where frame time per frame increased to around 20.8 milliseconds. In both of these examples, the GPU is taking exactly the exact same amount of time of 8.3 milliseconds to render out the ray tracing. With ray tracing here, we get a more accurate look into the cost for that effect on these imaginary GPUs with less subjective distortions that frame rates or percentages could have. So the first type of effect I want to start with in this video is one of the simpler ray tracing effects that there is, and that would be ray trace shadows as found in Call of Duty, Cold War Black Ops, and Dirt 5. One is an Nvidia backed title, and the other one is an AMD backed one. Here I describe ray trace shadows as simpler, not because it's easier for developers to add, but because they can be computationally less complex. If you remember my video looking at the ray tracing from the pre-release version of Marvel's Spider-Man Miles Morales, I had this nifty graphic to show off various steps of ray tracing for ray trace reflections. I'm going to use this exact same graphic in this video for illustrative purposes. In step 1, the scene is prepared on the GPU and filled with all the objects that can potentially affect ray tracing. In step 2, rays are shot out into that scene and they traverse it to test if they hit objects. In step 2, this is where hardware acceleration comes in for both AMD and Nvidia. In the third step, the results from step 2 are shaded, like the color of a reflection, or whether a pixel is in or out of shadow. And in the last step, the result is smoothed over and cleaned up with denoising. For ray traced reflections or global illumination, each of these steps can be rather intensive. But for ray traced shadows, the shading aspect can be more simple due to the on or off nature of shadows or their grayscale nature. And step 2 can also be less intensive with ray traced shadows due to how straightforward the rays will move with ray traced shadows. So Dirt 5 I think shows off this simplicity well. When using the game's benchmark and averaging the frame times over multiple runs, it is possible to see how turning on the game's DXR ray trace shadows on the RX 6800 XT here leads to an increase of 2.4 milliseconds of rendering time on average. As we'll see in comparison to other effects, this is actually not that expensive. On the RTX 3080 here in the benchmark over multiple runs, the average rendering time increased per frame by 2.1 milliseconds with RT on. So the RTX 3080 is rendering these shadows marginally faster than the RX 6800 XT. Going over to Call of Duty Black Ops though, the story gets more interesting as that game offers more separate shadow options with various quality levels. On the RX 6800 XT, going from off to medium ray traced local shadows, so those from artificial light sources, increases rendering time by 3.1 milliseconds. And from medium to ultra by a further 1.8 milliseconds. The RTX 3080 here from off to medium sees an increase in rendering time of 1.2 milliseconds and a further 0.7 milliseconds in this scene when going from medium to ultra. So local RT shadows render faster initially on the 3080, and increasing their quality does not dramatically increase the rendering times as it does on the 6800 XT. Outdoor shadows here show a similar experience where going from sun shadows off to on at medium increases rendering time by 4.9 milliseconds on the 6800 XT. And going up to ultra increases the rendering time further by 1.9 milliseconds. On the 3080, turning on shadows here to medium increases rendering time by 3.2 milliseconds. And going up to ultra has a further 0.3 millisecond average increase in rendering time. So much like the local shadows here, the initial hump of turning them on is higher on the AMD card, and increasing quality going up to ultra has a higher cost as well there. I think it's interesting to note here though, how the rendering time advantage here with turning on sun shadows is less on the RTX 3080 than it was with local shadows. And I think a possible reason for this can be seen when we look at our ray tracing steps. See, local shadows require a smaller scene to be built up in step 1 than with sun shadows. So other parts of the pipeline with local shadows have a greater weight on the performance difference, as step 1 is less important in comparison. RT shadows from the sun though require most of the entire game scene to be prepared in step 1. So step 1 becomes more expensive. So differences in performance from areas later in the steps, like step 2, 3, and 4 then become comparatively less significant. So by looking at shadows here, I think we already have hints that performance differences between these GPUs may be coming from between steps 2 and 4. The next effect I want to take a look at are ray traced reflections in Ghost Runner and Watch Dogs Legion. Now here there's no AMD sponsored title that has ray traced reflections yet, but I think both of these picks are still sound. For one, Watch Dogs Legion has a good console version utilizing ray traced reflections, and the RX 6800 XT is of course a much more powerful GPU than those found in the Series X or PlayStation 5. My only trepidation is that Watch Dogs Legion uses an Nvidia denoiser, but I'll get to that at the end of this video. Ghost Runner I find to be reasonable because it's using a multi-platform engine in Unreal Engine 4, but also because it's one of the few titles available on PC where we can go in there with some modding in Unreal Engine 4 and turn on and off individual parameters that affect ray tracing. So we can use these parameters to get a better understanding of what is actually costing so much in ray tracing. So let's start first with that. Here in Ghost Runner in this scene, the RX 6800 XT, turning on ray tracing at quarter resolution mode increases rendering time by 4.0 milliseconds. So already here in Ghost Runner, you can see how much more generally expensive ray traced reflections can be than ray traced shadows, even when they're in a compromised resolution form. At the default full resolution, the rendering time is increased by a further 2.8 milliseconds on this RX 6800 XT. So a total of 6.8 milliseconds here for the RT reflection effect at its default 100% screen resolution quality as found default in the game. On the RTX 3080, turning on RT at this quarter resolution costs 3.0 milliseconds of more rendering time, and going up to its full default 100% resolution increases rendering time by a further 1.7 milliseconds for a total of 4.7 milliseconds. The differences in performance here are interesting, and I think we can go back to our steps. So just turning on the effect here at quarter resolution has every bit of this pipeline working, of course. Yet increasing the resolution by going up to 100%, quadrupling the amount of resolution and rays increases the performance costs of step 2 and 3. So by increasing the ray traced resolution and looking at GPU performance here, we're seeing the effects in the differences of hardware acceleration in step 2, and also the effect of differences in raw GPU shading power in step 3. Looking at our numbers again, increasing ray traced resolution by 4 times increased rendering time by 2.8 milliseconds on the 6800 XT and 1.7 milliseconds on the 3080. So the 3080 is either managing step 2 better with its hardware acceleration or step 3 better with shading, or a combination of doing both step 2 and 3 better. I think we could try and isolate this effect by another tweak by increasing the amount of samples per pixels of these reflections. Basically here, with this modding tweak, I can make the reflections shoot more rays per pixel to better inform their shading and reduce the amount of noise. If we look at our step-by-step guide, this will have a very large effect on step 2. On the 6800 XT, increasing samples per pixel to 2 above the default 1 increases rendering time by 3.3 milliseconds. Doubling that to 4 samples per pixel increases rendering time by a further 7.2 milliseconds. On the 3080, doubling to 2 samples per pixel increases rendering time by 1.6 milliseconds, and increasing to 4 samples per pixel from 2 further increases rendering time by 4.4 milliseconds. So with this change to the settings, we have better isolated the cost of step 2. In that doubling of rays for these mirror-like reflections, the RTX 3080 calculated those rays in half the time of the 6800 XT. Quadrupling the rays though for such mirror-like reflections only rendered 75% faster on the 3080. So it looks like somehow the advantage of that GPU starts eroding as the ray count increases to much higher levels. The last area I want to test here on Ghost Runner is the effect of more divergent rays, as they're called. So when rays move more randomly. We can do this by increasing the maximum roughness at which reflections occur. So more rough materials are then included to get rough looking reflections. Looking at our steps again, this does quite a lot to our steps actually. Firstly, in step 2, more rays are going to be shot out in total as more surfaces on screen are allowed to have rays tested against them. Furthermore, in step 2, those rays that are now hitting rougher surfaces are going to be a bit more chaotic, a bit more random, so they'll offer a further challenge to hardware acceleration. And lastly, step 3 now will also get more expensive as there's going to be more surfaces to shade. Increasing the maximum roughness from default 0.2 to 0.4 increases rendering time by 5.5 milliseconds on the 6800 XT. From 0.4 to 0.9, and nearly every surface on screen is having a ray shot against it and tested and shaded. Rendering time is further increased by 9 milliseconds. So yeah, this is really expensive. On the RTX 3080, going from 0.2 to 0.4 roughness increases rendering time by 2.7 milliseconds. From 0.4 to 0.9 by a further 7.1 milliseconds. That initial increase to 0.4 roughness max is rendered in less than half the time on the RTX 3080. Yet pushing that further to max roughness 0.9 sees that advantage efficiency drop, where the increase there is handled in total a little less than 50% faster on the RTX 3080. So like we saw with increasing ray per pixel, the RTX 3080 almost looks like it has a peak advantage over the RX 6800 XT that lessens after a certain threshold of ray tracing. Moving on to Watch Dogs here, these tests will show a different area of scaling as ray tracing quality settings in Watch Dogs primarily only affect step 1 and 2. Per default on PC, the ray trace reflections in Watch Dogs have a very high max roughness value, and this cannot be changed in the menus, and the resolution and samples per pixel cannot be changed as well. So the rays being shot out are going to be rather random by default with these type of reflections, and there's going to be a lot of rays since so many objects, even the roughest ones, are going to be affected. Changing the RT quality options in this game from medium to ultra instead increases the size of the game world maintained in step 1 and increases the amount of objects present in that game world. The more objects then further into the distance means rays will have to spend more time going into the distance to traverse and find more objects. Furthermore, the ultra ray tracing setting above high here includes particles and ray traced reflections. And the way particles are handled in ray tracing makes step 2 more expensive, even with hardware acceleration. Here, by utilizing the game's benchmark and running it multiple times, I was able to see how turning on ray tracing to medium on the 6800 XT increases rendering time by 10.2 milliseconds. By comparison, the RTX 3080 managed that in a little more than half the time at 5.3 milliseconds. Increasing from medium to high further increased rendering time by 2.7 milliseconds on the 6800 XT and by 1.0 milliseconds on the 3080. And by adding even more objects and including particles on this ultra setting, the rendering time was further increased by 2.6 milliseconds on the 6800 XT and by 0.9 milliseconds on the 3080. So the 3080 here, by turning on these very high roughness reflections, is running almost twice as fast as the 6800 XT. The last effect I want to investigate here is Ray Trace Global Illumination, and for this I've chosen Metro Exodus as it does the effect very well, and it's one of the few titles that actually has implemented this, and QUAKE 2 RTX, as that is one of the few other titles we have that have implemented a version of Global Illumination. Now, looking at our ray tracing steps again, Global Illumination is interesting as it's brutal on every single step here, much like Ray Trace Reflections is. But GI is different in step 2 compared to Reflections, where Global illumination means every extremely rough surface out there is going to be bouncing light, and bounced light can come from nearly every direction, not just straight on, more simply like you would see with reflections. So the rays used for GI are very, very random. This makes step 2 particularly hard computationally, where hardware acceleration kicks in to traverse these chaotic rays in the scene. In Metro Exodus, the ultra quality setting above the high setting doubles the amount of rays shot out and therefore shaded, and thus it also affects steps 2 and 3 when turning up to ultra. But it also, this ultra setting, doubles the resolution at which denoising occurs in step 4. It goes from checkerboard to native resolution essentially. On the 6800 XT, turning on RTGI to high increases rendering time by 5.8 milliseconds. On the 3080, rendering time is increased by 2.8 milliseconds. Increasing RTGI to full resolution on Ultra increases rendering time by 2.3 milliseconds on the 6800 XT and by 1.9 milliseconds on the 3080. So interestingly here, the initial hump of enabling GI at a lower resolution is rendered in half the time on the 3080. Yet further increasing the amount of rays above that and increasing the denoising and increasing the shading is only 20% faster. Moving over to QUAKE 2 RTX, we're looking at an even more extreme case of global illumination, as the game is already rendering most of the other elements in the scene via ray tracing. So hardware acceleration is already being really utilized in QUAKE 2 RTX. But without GI, QUAKE 2 RTX's ray tracing is not exactly very random. The rays are moving more coherently, more straight. Adding in global illumination on top of the default rendering without it increases the amount of rays, and those added in rays are going in completely random directions. So in this scene here, turning on global illumination, as you see in the middle here, adds in this bounce lighting and shading into this shadowed corner. The game without global illumination on the left just flatly shades these regions with a more or less static diffuse color, and metallic objects stay essentially black. On top of this, the ray trace setting on the highest on the far right adds in a second bounce of GI to further brighten up dark corners. By turning on GI here, the RX 6800 XT adds in 5.1 milliseconds to rendering time. By adding in the second bounce, rendering time is further increased by 2.7 milliseconds. On the 3080, turning on GI increases rendering time by 1.7 milliseconds, and the second bounce incurs a further 2.0 milliseconds of rendering time. Here we're seeing a similar pattern like we saw before with ray trace reflections and the GI in Metro Exodus, where activating the effect at a lower rate count sees the 3080 performing much faster. It renders it actually here 3 times as fast than the 6800 XT, but increasing the amount of rays above that comparatively sees a lessened advantage, where that additional bounce is rendered in 25% less time on the 3080 than the 6800 XT. So those are essentially all the effects that I want to test, but it's not my last test. Looking at our steps again, I'm actually curious about the cost of the denoising step, the last one. This can be very expensive in its own right, as ray tracing is really noisy unless the GPU comes in to smoothen it out while also making the image actually look like something instead of just a blur. There are not a lot of games which actually allow you to toggle denoising on and off, but it's toggleable in the menu in Quake 2 RTX, and you can also turn off and change the denoising in Watch Dogs Legion through modding. In Watch Dogs Legion, the game ships with an Nvidia GameWorks Reflections denoiser. In this scene here, I have first turned it off, which has no denoising other than the TAA in the game, and there's a lot of sparkling. Hidden inside the game files, there's a denoiser 1 as it's labeled, which is the value that next generation consoles use. This denoiser 1, as I will call it, clears up a lot of the noise, but there's still some noise left if you look on the edge of metal, like the letters here. This denoiser at times also does not reconstruct transparent reflections very well, so reflections on glass can look a bit pixely as you see here. Then there's the 2 value for the denoiser hidden in the game files, which is the default denoiser and probably corresponds to the Nvidia GameWorks one. This further cleans up the noise above denoiser 1, so you can see how the metal letters here no longer have flickering on their edges. Also, transparent reflections reconstruct in a less pixelated manner with this denoiser over the first one. Turning on denoiser 1 on the 6800 XT incurs a rather severe 3.9 millisecond increase in rendering time. On the 3080, rendering time is increased by 1.5 milliseconds. Turning on the number 2 GameWorks denoiser, the RX 6800 XT increases rendering time by 2.9 milliseconds in comparison to off, while turning on this denoiser on the 3080 increases rendering time by 2.5 milliseconds in comparison to off. So the number 1 denoiser runs a lot slower for some reason on the 6800 XT, and the number 2 denoiser runs only marginally slower there. Quake 2 RTX is a slightly different story, as the denoiser in that game is going to be very heavy as it makes the game look at all like a game. Using a demo benchmark I have made, I was able to determine that this so-called ASVGF denoiser in Quake 2 RTX costs about 6.3 milliseconds on average on the RX 6800 XT at 1440p. This is in contrast to the 3.7 milliseconds cost of that same denoiser in the same benchmark at that same res on the 3080. The reasons for this could be manifold, is why we're seeing a performance difference here. But this is just pure compute, so I'm not sure why this is running slower or faster on one GPU. This type of denoising is not exactly common though, as it's only really found in Minecraft RTX and this game. So it's not very generalizable about the cost of denoising, I would say, across a variety of titles. So there we have it, a variety of tests, different titles, 3 different effects, and the cost of denoising. And I still think, in spite of this smaller N size, there are some generalizable trends here. Ray tracing used for shadows is generally cheap on both the 6800 XT and the 3080. The 3080 seeing minimal wins at lower settings, which then increase as ray tracing quality is increased as well. For ray traced reflections, we can see that this effect is generally just more expensive than ray traced shadows. Yet here is where the visible differences became more evidenced. The higher randomness of the rays of the reflection, or the higher amount of rays shot out, meant there was a greater performance advantage for the RTX 3080 in comparison to the 6800 XT, rendering in nearly half the time in certain configurations. 3080's efficiency, though, lessened after a certain tipping point. That lessened efficiency advantage was also seen with global illumination, where the RTX 3080 could render the effect in nearly half the time in Metro Exodus, or nearly 1/3 the time in Quake 2 RTX, yet increasing the amount of rays after just turning it on saw that RTX 3080 advantage decrease. In general, from these tests, it looks like the more simpler the ray tracing is, like shadows, the more similar the rendering times will be across these GPUs. And the RTX GPU above this with more complex effects just seems to have a less dramatic performance loss. The caveat I will place here is that these are still just a limited number of games, so the trends may not always be viable across other titles. And I hope in the future that I can test more games, specifically AMD sponsored titles that will come out in time, as I want to show off more effects than just ray traced shadows, which is so far the effect that these AMD sponsored titles have chosen to use. It would be nice to see more complex effects like reflections or GI from an AMD sponsored title to see how those scale differently than those we've seen in something like Watch Dogs or Metro Exodus. But that is as much as I can say now reasonably for these tests. If you did like this video and you found you learned something from it, please hit that like button and subscribe to the channel. If you're already a subscriber, then hit that little bell in the corner to be informed as soon as Digital Foundry posts a video. If you want to see this video in higher quality than it's found here on YouTube, support us Digital Foundry on Patreon to get years worth of Digital Foundry content available in high quality for download. Want to talk to me about this content in this video? Write a comment below or follow me and Digital Foundry on Twitter. As always, this is Alex, bidding you farewell und auf Wiedersehen.